Hey everybody, welcome to another lecture in logic. And today we're going to talk about logical, well maybe we will if I can get it out of my mouth. Today we're going to be talking about logical equivalence. There, I did it. Two statements, P and Q, are logically equivalent, or just equivalent, exactly when they have the same set of truth values as displayed in their respective truth tables. And let me close the parentheses here. So if their truth tables display the same set of truth values, then the statements are logically equivalent. So let's look at an example. Consider the statement not P or Q. And we'll do the truth table for that. We have P, we have Q. So there are four possible combinations of truth values. We go true, true, false, false. And then we go true, false, true, false. These are all the possible combinations of truth values of P and Q. Each different combination of truth values of P and Q is displayed exactly once. Now let's see. We want the truth values for not P or Q. So I guess the first thing we have to do is get the truth values for P or Q. And this is an OR statement. What's the special case for an OR statement? Let's see. An OR statement is only false when both statements that make it up are false. So let's see, where are P and Q both false? Right here, right? They're both false here. So this set of truth values of P and Q, the statement P or Q is false. In all other situations, the statement P or Q is true. Now we want to look at the negation of this, not P or Q. And remember what a not symbol does, or a negation symbol does. It changes true to false and false to true. So we have true becoming false, true becoming false, true becoming false, false becoming true. So these are the truth values for not P or Q. Now let's consider another statement. Let's consider the statement not P and not Q. We'll do a truth table for this statement also. So I guess the first thing we have to do is prime the pump and set the truth table up. So we're going to have true, true, false, false for P, and true, false, true, false for Q. This gives all the possible combinations of truth values for P and Q. And before we can perform AND on these two statements, we have to compute not P and not Q. This negation sign just changes the the true values for P to falses, and it changes false values to true. So true, true becomes false, false, and false, false becomes true, true. So these are the truth values for not P. We also need truth values for not Q. So we look at the truth values for Q, and we change trues to falses. And we change false to true. So there are the truth values for not Q. And I think we're ready to join these two things together with the AND operator. So we have not P and not Q. This is an AND statement. What's the special case with an AND statement? Think about it. An AND statement is only true when both of the statements that make it up are true. So when not P and not Q are both true, then this whole thing is true. And that happens right here, doesn't it? Not P is true, not Q is true. So the whole statement is true. Every other time it's false. So these are the truth values for the statement not P and not Q. And guess what? The truth values for this statement, false, 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 true, are exactly the same as the truth values for this statement, false, 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 true. Son of a gun. I'm going to make a note of that. They're the same. So I think there's something that we can conclude from this, and I'm going to write that down. Those two statements are logically equivalent. Now, that statement This symbol means is logically equivalent to. So the negation of P or Q is logically equivalent to not P and not Q. And I guess maybe I want to comment on that in just a second. In our previous example, we showed that these two statements were logically equivalent. And this is one of DeMorgan's laws for sets. There are two DeMorgan's laws for sets. And the first is that the negation of an or statement is an and statement. And here's how we do it. If we negate an or statement, then we take the individual simple statements P and Q and we negate each of them. And then we change the or to an and. So to negate an or statement, negate each of the individual simple statements, and then change the or to an and. And the analog works as well. The negation of an and statement is an or statement, and we do it this way. To negate an and statement, we negate each of the simple statements that make up the and statement. And then we change and to or. These two things are called DeMorgan's laws for sets my foot. DeMorgan's laws for logic. I wonder why I was thinking of DeMorgan's laws for sets. What do you think? We did learn DeMorgan's laws for sets, didn't we? And we learned that the complement of a union was the intersection of the complements. Wow, how about that? And the complement of an intersection was the union of the complements. There's a very close correlation between DeMorgan's laws for sets and DeMorgan's laws for logic. These are DeMorgan's laws for logic. DeMorgan's laws for sets have to do with taking complements of intersections and unions. These two things we should know. They'll prove helpful. Now let's look at a couple more examples. Okay, let's take these two. If P then Q, or P implies Q, and not P or Q. Our assignment, should we decide to take it, is to determine whether these two statements are logically equivalent. And I think the only weapon that we have in our arsenal right now is just to do a truth table for each one and to see if the truth tables match up. So let's do that. P implies Q. Well, we know what that is, don't we? P, Q. See, for P, we go true, true, false, false. For Q, we go true, false, true, false. And let's see, P implies Q. We've seen this truth table before, and we know it has a special case. What's the special case for an if-then or an implies statement? The only time that an if-then or a P implies Q statement is false is when? When we have P true implying Q false, right here. This is the only time that it's false. All of the other times, it's true. Now, let's do this rascal. P, Q, true, true, false, false, true, false, true, false. Okay, we've primed the pump. We've set the truth table up. And it looks like the first thing I have to do is get a column of truth values for not P. So if I negate P, I change the truths to falses. And I change the falses to truths. There. Now I guess I have everything else I need. I have Q, I have not P. I'll just put these two together with an OR. Not P or Q. And let's see how this turns out. This is an OR statement. What's the special case for an OR statement? The only time an OR statement is false is when both of the statements that make it up are false. Does that happen here? Let's see. Not P and Q, are they ever both false? Yeah, they are right here. So in this case, when not P and Q are both false, the whole thing is false. And this is the only time that that happens. All of the other times, this statement is going to be true. And are they the same son of a gun? They are. Those two things are the same. So we will write, since the statements P implies Q and not P or Q have the same truth values, they're logically equivalent. So I guess maybe I can put the icing on the cake here and write P implies Q is logically equivalent to not P or Q. Okay. This is a nice exercise. And instead of using truth tables to do this one, we're going to use the results of the previous exercise. So let's write down what we determined in the previous exercise. In the previous exercise, we determined that the if-then statement, if P then Q, is logically equivalent to the statement not P or Q. This is what we determined in our last exercise. Well, if these two things are equivalent, then their negations would have to be equivalent also. So let's negate both of these. Negation of P implies Q, which is what we're looking for. And that's going to be logically equivalent to the negation of not P or Q. Well, I'll tell you what I notice here is that this is the negation of an or statement. And DeMorgan's laws tell us how to do that. So I'm going to say these are logically equivalent by DeMorgan's laws. The negation of an or statement is an and statement. And here's how we do it. We take each individual simple statement, not P and Q, and we negate these two things. So we take the negation of not P and the negation of Q, and we change the or to an and. Now, what happens if we negate a statement and then we negate it again? We just get the original statement. And here's how we can reason on that. If we negate P, all of its true values are changed to false and all of its false values are changed to true. And if we negate it again, all of the false values are changed back to true and all of the true values are changed back to false. So this is logically equivalent to P and not Q. So this thing and this thing are logically equivalent. So here's how we negate an if-then statement. The negation of P implies Q is P and not Q. Now, is that something that's hugely important? I don't think so. It makes for a good exercise, but is it terribly important? I don't think this is something we have to remember. And quite honestly, the result of the previous exercise, it's a nice exercise, but I don't think we really need to memorize this either. DeMorgan's laws, yes, we do have to memorize those. This, I don't think we need to know. And this, I don't think we need to know that either. I'm not a big fan of memorization. Some things we absolutely have to memorize, and those things I say, memorize them well. But there is such a thing as the straw that broke the camel's back, that we don't want to have to memorize everything in the world. So this is nice. I don't think we need to memorize it. This is nice. I don't think we need to memorize that either. Okay. I told you some things that were worth memorizing, DeMorgan's laws. I told you some things that probably weren't worth memorizing, the results of our previous two examples. Here's something that's worth knowing, and for good reason. Given the conditional statement P implies Q, or if P then Q, there are four variations on this statement. One thing that we can do is we can turn it around and form the statement Q implies P, or if Q then P. Another thing that we can do is we can take the original conditional statement and negate the first and negate the second. So we have not P implies not Q, or if not P, then not Q. And we call this thing the inverse of the conditional. The statement that we formed by taking P and Q and just reversing roles to get Q implies P, we call that the converse of the conditional. And then there's this thing. Here we take the original conditional statement and we swap P and Q, and then we negate them. So we put Q over here and negate it. We put P over here and negate it. And we call this the contrapositive. Now, some of these are more important than others. The inverse, I'll tell you what, we don't do too much with this. The converse, that's fairly important. Here, P being true implies Q being true. We might wonder when the case is where Q being true implies P being true. That would be the converse of the original. And this thing, the contrapositive, it looks rather torted, sort of screwed up, but this is actually very important. I'm not going to tell you why just now, but I will tell you. As a matter of fact, in about 5 minutes, I'll tell you, okay? Let's do an example. Here's our next example, and hard as I tried to get this all on one line, I couldn't. But here's why the contrapositive is important. We're going to show that the conditional statement, P implies Q, is logically equivalent to its contrapositive, not Q implies not P. So in other words, they're the same statement, they just look different. So let's see, how do we show that two statements are logically equivalent? One way is to show that they have the same truth tables. And that tool is always in our toolbox. And that may be the best way to do this. P implies Q. We know the truth table for that, don't we? True, true, false, false. True, false, true, false. And let's see, this is an if-then statement or an implication. When is the only time that an if statement, an if-then statement is false? That's the special case, right? The special case with an if-then statement is the one case in which it's false. And when's the only time that P implies Q is false? Do you remember? P implies Q, the special case. When is it false? Exactly when we have P true implying Q false, right? Whenever we have a true implying a false, that's going to be false. And here P is true and Q is false. So this is the case when our conditional statement is false. In all other cases, it's true. So I don't even have to think about it. I just go true, true, true. Bingo, I'm done. Now, let's do the truth table for this joker. Again, we have P and Q. And before I start on that, let me just finish up and circle the column of truth values for the statement P implies Q. Okay. Now it looks like we need not Q and it looks like we need not P before we can join them together. So let's do not Q. And this negation sign changes truths to falses and false to truths. Funny thing though, I don't see truths and falses here. I better put some up here, huh? Okay, true, true, false, false, true, false, true, false. There we go. And this negation sign in front of the Q changes the truths to falses. So true goes to false, true changes to false, and the negation sign changes falses to truths. False becomes true, false becomes true. So we got the column for not Q, and we're going to need a column of truth values for not P as well. Okay, not P. This changes truths to falses. And it changes falses to truths. So we just negated not P, or we just negated P. And I think we're ready for this thing. We're going to join them with an if-then. Not Q. If not Q, then not P. There we go. This is an if-then statement. What's the special case for an if-then statement? The only time that an if-then statement is false is when what? We have a true implying a false, right? Does that happen? Right here it does. Not Q true and P false. And that's the only time it happens. We have true implying false, so that's false. All of the other times the statement's true. I don't even have to think, and that's great. I hate to think if I don't have to. Now, my whole purpose in creating these two truth tables was to show that the statement P implies Q and its contrapositive, not Q implies not P, have the same truth values. And I'll be a son of a gun. True, false, false. No, true, false, true, true. True, false, true, true. They're the same. So I'll sum it up. Since the conditional P implies Q and its contrapositive not Q implies not P have the same truth values, they are logically equivalent. Now, this is something well worth knowing. Very important. And the reason that it's important is sometimes a conditional statement may be difficult to work with, and its contrapositive may be a lot easier to work with. And so if we can show that something is true for the contrapositive, that something will also be true for the conditional statement. So again, the importance of the contrapositive is that the contrapositive may be a lot easier to work with than the original conditional statement. And if that's the case, we'll work with the contrapositive instead. And whatever we show to be true for the contrapositive is going to be true for the original conditional as well. Now let's summarize this. This is what we just showed. The conditional statement, P implies Q, is logically equivalent to the contrapositive, not Q implies not P. These two things are logically equivalent. And this is very important. It's also true that the converse is logically equivalent to the inverse. That is, Q implies P is logically equivalent to not P implies not Q. Oddly enough, even though this relationship holds, it's not nearly as important as the equivalence of the conditional and its contrapositive. So this is the big result we take away. The original conditional and its contrapositive are logically equivalent. It's also true that the converse and the inverse are logically equivalent, but these are not terribly important, believe it or not. You would think that maybe they'd be just as important as this, but we very rarely use this relationship. This is the biggie right here. So know what the conditional is, know what the contrapositive is, know what the converse is, that's important, and know that the conditional and the contrapositive are logically equivalent. This is a big relationship right here. So remember that. Okay, let's do an example. Let's see, we have two roommates who are fighting here, or maybe boyfriend and girlfriend who are fighting. We want to write the contrapositive of the statement. If you don't let me use your cell phone, then I won't let you drive my car. Now, it is a conditional statement. Whoops. There we go. So, if you don't let me use your cell phone, that's P. Then I won't let you drive my car. I won't let you drive my car, that's Q. And the contrapositive is going to be not Q implies not P, or if not Q, then not P. So So I guess the first thing we have to do is negate Q. What's the negation of I won't let you drive my car? The negation is I will let you drive my car, right? So if I let you drive my car, comma, then, so here's not Q. I will let you drive my car, or I let you drive my car. Now we have to negate P. How do we negate you don't let me use your cell phone? You will let me use your cell phone, right? Now let's see. If I let you drive my car, then you will let me use your cell phone. Not Q implies not P. And the most important thing is they lived happily ever after. That will conclude the lecture for today, and I will send out some homework exercises to do from the text and also from my math lab.